Today's lecture is entitled The Early Universe. I want us to consider what we can see, how we can see it, and how we can use those observations and measurements to infer back to the beginning of our cosmos and how it evolved at some of the earliest times. So I want us to begin by considering the question, what are our horizons and how far back can we see? Well, I'm sure it will be very obvious when we consider what our horizons are, that would depend on our vantage point and the information we can detect and when we look for that information. So I'm showing here a photograph of a road I was driving along in Chile, in the Andes, towards my observatory in Chile one day. And I got out of my car seeing this rather beautiful sunset. You won't be surprised to hear me say that different parts of this image are different ages. The snowclaps and on the distant mountains and the clouds are ephemeral. The pink light of the sunset even more so. It disappeared 5 minutes after I took this photograph. But the mountains in the foreground and in the far distance, those are a few tens of millions of years old. By analysing those old mountains, we can understand the geological activity that led to Chile being the shape it is today. And so it's a principle that I want to draw out, that by studying the oldest things that we can see within our horizon in the universe, we can gain information about the earlier times. So let's now turn our attention to what is the oldest thing that we can see in the universe. Well, the oldest thing that we can detect in the universe is radiation. We call it background radiation. And this radiation that I'm going to be speaking of today was emitted from the hot, swirling plasma soup that all the galaxies and stars that we see around us today were originally formed from. To understand the information that we can glean from the oldest radiation in the universe is to learn about the origins of the cosmos, its ingredients, and, as we'll see later on in the talk, its fate, the fate of the cosmos itself. So this primordial radiation that I'm going to be speaking about quite a bit today parted company with the hot matter that emitted that radiation a very, very long time ago. When I say a very long time ago, we think that the universe is something like 14 billion years old, and we think that the radiation that I'm talking about today was emitted some 300,000 years after time itself began in an event in the history of the universe that we refer to as the Big Bang, the hot Big Bang itself. So that is the oldest thing that we can hope to study. And it dates back to 300,000 years, 3,000 centuries after time began. So what is this radiation? What are we looking at exactly? Well, where you have regions in this primordial plasma soup, and by plasma soup I mean a swirling porridge of protons and electrons and things that are on their way to becoming the cold atoms that we know about today. In that swirling around of the plasma, there are overdense regions where there's a bit more matter than there is in the underdense regions where things are a bit more spread out. In those overdense regions, gravity will do its stuff. Gravity will attract a bit more matter towards it, and so it will become overdense. And then, being a bit more overdense, having a bit more matter associated with it, gravity will continue to attract yet more matter. So those regions of space will become even more overdense, extracting matter from the underdense regions that are nearby. That's gravity for you. But how those overdensities of matter then turn into the beautiful spiral galaxies that we know and love from observations today will be the subject of my lecture in January. So not much in the way of pretty galaxies today, I'm afraid. But that swirling plasma soup, which leads to the formation of structures like galaxies, like clusters of galaxies, is precisely the plasma that we're talking about that releases the radiation that's the subject of today's lecture. By radiation, I mean light or photons. A photon you can think of as a quantum of light, a packet of light energy. How much light you see and what the wavelength or the colour of that light is depends on exactly how hot that plasma soup was. Now, we have good reason to believe that the universe has been expanding since the earliest times. I'll touch on that a bit more later on in my lecture. But if you do accept with me that the universe was expanding, it necessarily follows that as the universe was expanding, it was also cooling down. The temperature was dropping and dropping as the expansion happened. But there came an epoch, there came a point in time, believed to be about 3,000 centuries after the Big Bang, when the temperature became sufficiently low and the density became sufficiently sparse that all the atoms around at the time ceased to interact with the radiation. Thereafter, the matter that was there was completely transparent to that radiation. And so the key point is this: that radiation has been travelling since 3,000 centuries after the Big Bang until now, when our receivers and telescopes can detect it. This radiation is what we know as being the cosmic microwave background radiation. How do we measure it? How do we see it? Well, let me tell you just a little bit more about the nature of that radiation. The wavelength of the radiation that we're talking about is about 1 millimetre. That's why we call it microwave radiation. It's a little bit shorter than the electromagnetic waves that rattle around in your microwave oven at home. Microwave refers to quite a broad band within the electromagnetic spectrum. So that's where you see most of this radiation, with wavelengths of a few millimetres. That sort of radiation is not sufficient to blast apart atoms. It hasn't got enough energy to do that. But it has got enough energy to make water molecules rattle and vibrate. And so if you try searching for this relic radiation from a very damp and humid place with lots and lots of water around, chances are you won't detect any cosmic background radiation at all, because all the water molecules above you in the atmosphere will absorb the radiation that's shining from those distant parts of the universe, and we just won't see it. It will be absorbed by local, relatively local water molecules. So if you want to detect this cosmic background radiation, you either need to fly a balloon to above the atmosphere, preferably in a place that's very, very dry, such as Antarctica, or, better yet more expensive, is to fly a satellite well above Earth's atmosphere and well above any molecules that might attenuate or absorb the very radiation that we are trying to find. These are pictures here of some of the balloons and some of the satellites that have flown in recent times and made measurements, quantitative measurements of the cosmic background radiation. I'll show you some of the data that they have collected. But first, I want to do a little bit of expectation management about what such early radiation might look like. Now, 3,000 centuries might seem a long time, and it is relative to our own human experience, but it is not enough time to form one of those pretty spiral galaxies that we'll be hearing about in January's lecture. So when we do examine and record and image this primordial radiation, we're not going to see any galaxies. We're going to see overdensities and underdensities that ultimately will give rise to galaxies, but they're not going to be very, very pretty. All we're going to be seeing is the overdensities, the underdensities, the hotter regions, the cooler regions within that plasma. I hope I've sufficiently lowered your expectations that what we're about to look at isn't actually that pretty. In fact, here we are. Multicoloured porridge is pretty much the kind of thing that we're looking at. This is just a relatively small region of sky, about 30 degrees by 20 degrees or something like that, taken by one of the satellites that I was referring to. So you may think that's a bit nondescript, and indeed you might be tempted to think, erroneously, that it's devoid of information. Not a bit of it. There's a lot of physics information in there which speaks very directly to the processes that must have happened at the very earliest times. And I'm going to switch units of time now from centuries to seconds, and indeed fractions of a second. Those are the timescales these data tell us about. But first, let's orient ourselves with what we're looking at. I'm going to show you an image now of, I hope, some of your favourite constellations projected on a map of the sky in a slightly different projection from maybe how you've seen them in the past. So perhaps those nearer the front can see some of their favourite constellations. One of mine down here on the lower right is Carina. I love that constellation. I will talk about it for hours if sufficiently provoked. We've also got Aquila and we've got Cygnus. And a constellation I've been working a lot in the months since we've been apart is Ophiuchius. So this is a map of all the constellations that we know and love, as well as probably some of the constellations that we haven't necessarily heard of. And the particular type of sky projection is referred to as that of the galactic coordinate system. So the big stripe across the middle corresponds to the plane of our galaxy, the Milky Way itself. The very centre of the Milky Way, the galactic centre, is bang in the middle of this ellipse. And you can maybe just make out that Scorpius is right in the middle, SCO being the constellation containing the galactic centre. So I hope you're a little bit oriented, maybe, about where some of the stars that you may know of, Ursa Major and the Pole Star, are over in the upper left on this figure. What I'm going to do now is, with the exact same projection, show you what one of these satellites, the WMAP satellite, saw when it made a complete survey all around the sky, integrating over signals from all directions. So keep that in your mind. You've got the stripe in the middle, which is the plane of our galaxy, and this is what WMAP, the WMAP satellite, sees. So let's think about what we're seeing here. Well, we've got a great big red stripe that's coincident with what I said was the plane of our galaxy. And sure enough, as you may be suspecting, that red region is nothing to do with primordial radiation or any of this relic radiation that I've been introducing, but it's everything to do with what one might impolitely refer to as contaminating radiation from the Milky Way itself. So we don't really want that. We need to subtract that out, and that means a lot of careful modelling about what we think the brightness structures are associated with our galaxy. But you can perhaps already get a sense, if you look towards the south galactic pole at the bottom and the north galactic pole at the top, that if you could peel off the foreground contamination due to our galaxy, that you'd see something that actually looks pretty much uniform, homogeneous, the same kind of thing at the North Galactic Pole and at the South Galactic Pole. Maybe you might be seeing hints that the universe is homogeneous and isotropic. What do I mean by these polysyllabic words? Homogeneous means the same at every point. Isotropic means the same whether you look in that direction or that direction or that direction. We're seeing hints that the nature of the universe is homogeneous and that it's isotropic if we start to look at data like this. Now, of course, the notion that the universe is homogeneous, the same at every point, manifestly does not apply on the smallest size scales. A lecture theatre is not like being at the beach or in the desert. They're just different. The interior of a star is not like the interstellar regions of outer space. But when you get on sufficiently large scales, and I'm talking huge great regions containing thousands of galaxies, then we do think that the universe is the same in whichever direction we look and at every point we make the measurement. And it's data like these, you'll see now the galactic plane has been modelled and subtracted out. We do get a sense that that's a reasonable working assumption for the nature of the universe. So these data are now nearly 10 years old, something like that. The WMAP satellite finished all of its data analysis about a decade ago. The cosmic microwave background radiation is important because it helps us learn about the early universe. So let's now think about what some of those things are we can learn about the universe at the earliest times. The colour scale here actually maps to temperature, and that's something I'll be explaining in just a moment. What I want you to just absorb right now is that this blue, yellow, green, red porridge has got reasonably small scales on which you see variations. They're important because they hint at overdensities in the primordial plasma and underdensities in the primordial plasma. And it was the Canadian Jim Peebles who made the connection between the fact that if galaxies were going to form, if they were going to collapse under gravity and form in anything like a way that we could imagine describing with the laws of physics that we understand on the basis of experiments that we can carry out on Earth and on the solar system and that kind of stuff, he was the first person to point out there should be precursors of the galaxies that we see today if we can look back far enough to see back early enough in time. And sure enough, around the time that this paper was being written and developed, over in New Jersey, an antenna system was being developed which made one of the first convincing detections of the cosmic microwave background radiation that you saw in that elliptical projection on a couple of slides ago. So the most important thing to realise about the cosmic microwave background radiation is that it's there. It exists. These guys went to great lengths to make sure that they were detecting a real, true, extraterrestrial signal. They scrubbed pigeon droppings off their antenna to make sure that the dielectric properties of the pigeon droppings were not in any way skewing and contaminating their measurement. That's what's called making a thorough measurement is all about. Wherever they looked, outside of the plane of our galaxy, they saw the same thing. And ultimately, Penzias and Wilson, pictured here with their antenna, won the Nobel Prize for this discovery. Jim Peebles, of course, who I mentioned a few slides ago, who said, look, this has got to be there if we think that galaxies are subsequently going to form in ways describable, approximately describable by the laws of physics as we understand them. He won the Nobel Prize a couple of years ago for all of his contributions to physical cosmology. But the Nobel Prize that these two won, Arno Penzias and Wilson, was for the discovery itself. I'm going to show you a copy of their paper here. I hope you'll agree that there's a bit of an understated title on this important discovery. Measurement of excess antenna temperature, whatever that means, think of it as brightness, intensity of detection at 4080 megahertz. How about that for an understated title, which was to bring about the intellectual revolution between the pervading paradigm that the universe, the cosmos, was in steady state and utterly unchanging, with what is now the current paradigm that the universe began with a Big Bang. This is a seriously understated title. It's even printed over a page wrap. But despite this modest start, this paper, their discovery, completely revolutionized our thinking on the history of the cosmos. Because not only is the cosmic microwave background radiation there, not only does it exist, not only is it very uniform, it seems to look the same in that direction as in that direction, not only that, but if you take a spectrum of it, in other words, you say, how much intensity have I got as a function of wavelength, as a function of the colour of the light, if you like, it's got a very, very remarkable spectrum. And that spectrum is this shape. Now, if you happen to see my lecture last year on unravelling rainbows, you'll have heard me speak about a concept very familiar to physicists known as a black body. Now, physicists are all the time using everyday words and loading them with very, very specific meaning. And if you don't catch on to the fact that we're using very, very specific meaning, then it's very easy to get lost. But a black body is a theoretical concept that we have of a body that's in perfect thermodynamic equilibrium. Everything within it can mix and exchange energy until that energy is very, very evenly distributed according to the temperature that it's at. That's a very characteristic shape. And if you can make out any error bars on those data points through which that characteristic black body spectrum fits, let me tell you, those error bars are multiplied up by a factor of 400. These are exquisitely detailed measurements. To impressive precision, all over the sky, the spectrum is that of a perfect black body whose temperature is 3 degrees or 2.7 degrees above absolute zero. Another way of pronouncing that is to say that it's 270 degrees Celsius below the freezing point of water. We're talking seriously cold. That relic radiation from the earliest times is very cold indeed. But the precision of the shape of its spectrum screams out of a universe that's in perfect thermodynamic equilibrium. It's absolutely uniform. That's the shape you see whichever direction you point your satellite in. Where you see one of those little hot spots or one of those little cold spots in the green and blue porridge, all the emission is that shape, but maybe it's at slightly higher energies or lower energies, according to whether it's ever so slightly hotter or ever so slightly colder. More of that in a moment. But if you've got this very, very cold emission now, and if you accept that the universe is expanding and that as it expands, it cools, it follows that if you wind the clock back in time, the universe was previously much, much, much hotter. And so, the beginning of time we refer to not just as the Big Bang, but the hot Big Bang. Because we see the universe expanding now, more of that in a moment. We see that it's going to carry on expanding for time immemorial, more of that in a moment. But when we wind the clock back, we have every reason to presume that stuff was more and more and more condensed and hotter at earlier times. So there are various reasons for accepting the hot Big Bang as the appropriate paradigm for the mechanisms by which the early universe evolved. And one of the key tenets in that is the uniformity of the spectrum of the cosmic microwave background radiation. That was absolutely key, despite the very understated title of the discovery paper. But hey, they got the Nobel Prize later, so glory did come. It was absolutely pivotal thinking that that radiation was there and presented some of the necessary ingredients by which galaxies could subsequently form. But there are other pieces of the jigsaw that lead us to believe that the hot Big Bang is the correct model, the most appropriate model for the early universe evolution, given what we know at present. One of those, which I'll be touching on in my next lecture, is something called nucleosynthesis, where atoms get cooked up. And the ratios of these are hugely important, but very, very critically contingent on some of the details of the very early universe. The amount of lithium, for example, that we see in outer space, primordial abundances of lithium, so crucial for laptop batteries, by the way, is in exquisite agreement with what we think the details of the thermodynamic expanding model of the early universe actually comprises. Similarly, helium, so crucial for those helium balloons at birthday parties. The amount of helium that we observe in some of the oldest stars and so on agrees to exquisite precision with what these detailed models for the hot Big Bang actually predict. But so too is the expansion of the universe. And I want to discuss that a little bit more now, but I really want to emphasize the extent to which the hot Big Bang was a massive intellectual revolution for people who had come to think that the steady-state universe, the universe which was utterly unchanging and which would endure forever and which had always been thus, was absolutely swept away, not without some controversy and acrimony, but that's a completely different story. So just how smooth is this cosmic microwave background? Because that's an important part of the story. It's so extremely smooth that if you had ripples of the same amount, same fractional amount, same ratio on a swimming pool as you have in the cosmic microwave background radiation, you would find that the ripples on your swimming pool would only be 1/100th of 1 millimetre high. That's pretty tiny. So the cosmic microwave background radiation is really smooth. It tells us about when radiation decoupled from matter, when the universe became transparent to radiation, so it could travel on and on forevermore, when the universe was only a few thousand centuries old. The galaxy distribution, on the other hand, tells us much more about the current universe. But it's pretty clear the universe used to be, when we look back, a much more homogeneous place than it is now. And all of these different satellites tell a very, very similar story from one another. The most recent and the most modern satellites, WMAP on the left and Planck on the right, they give the same picture. You see, if you look at these two images and just compare them in your mind's eye, and imagine you're focusing the lens of a camera, you've got sharper focus on the right with the Planck satellite, the more recent one, than you have with the WMAP satellite on the left. That's essentially all the difference that's being seen by these two satellites, but they do, of course, corroborate one another. Well, this is the image from the WMAP satellite, and this is the exact same image from the Planck satellite. And although the colour scales are very slightly different, I hope you get a sense that you've got the same sort of features showing. Let's now turn our attention to the temperature scale on the bottom, the colour scale on the bottom, which tells us in what fine detail we've got these thermal variations. Over on the far left, coloured royal blue, we've got a marker at minus 300 microkelvin. A Kelvin is just a degree of temperature, same amount as a degree of Celsius. And on the right-hand side, we've got plus 300 microkelvin. So going from the bluest blue on the left to the reddest red on the right, we've got a span of less than 1,000th of a degree in temperature. I hope you'll agree with me that this demonstrates the jaw-dropping uniformity of that relic radiation all across the 4 pi of sky that we can observe if we're above Earth's atmosphere and whiz around in a satellite. Truly, the universe used to be a much more homogeneous place. It's interesting to ask the question, what are the size scales on which we do see these different coloured features in this multicoloured porridge? Well, I want you to imagine that you were asked to paint this, this image of data here, and you're given a load of paintbrushes of different sizes. And you can only use each paintbrush once. But every time you use a paintbrush, you have to stack it up so you keep track of what you've used. And you're given different sizes of paintbrush. So the one that you'll use the most, if you just look at the dots that you see most frequently, they're about a degree in size, it turns out. You'd use absolutely loads and loads of those relative to tinier scales still. And you'd sort of make successive dots, and you'd add up your paintbrushes, make another dot, take a long time. But you could think about how many paintbrushes of a degree do I use versus how many, a degree in extent, versus how many paintbrushes do I use with 1/10 of a degree. And you could histogram up all those different paintbrushes that you use in order to reproduce that data. And in so doing, you would have produced what we actually call, in our daily work, a power spectrum of the cosmological anisotropies of the cosmic microwave background. But let's stick with a histogram of the sizes of the paintbrushes. You'd have something like this. You'd have used most paintbrushes around a degree. You'd use vastly fewer paintbrushes at much smaller degree scales. The upper axis tells you about the angular scale in degrees. And so I'm drawing this to your attention because you do see a huge peak close to about a degree, and that turns out to have quite important physical significance that we will come to. So I may have been painting quite a rosy picture thus far, but I want to draw your attention to the fact we've got a bit of a problem with the data I have already shown you. And this is something referred to as a horizon problem. So our horizon is how far we can see in a given time. In my very first lecture, my inaugural lecture as Gresham Professor of Astronomy, I talked about, the title of that talk was Faster Than Light. The fact that we can't ever get information at a speed faster than the speed of light. And so if you say, well, time began here and light can travel this fast, then I can see out to this distance, can't I? Absolutely you can, in principle. That's what's called your horizon. But now consider this. How can the sky, that image that I just showed you, be so uniform all the way across when regions that are separated by more than, say, a couple of degrees cannot have been in causal contact with one another? How is it that the sky over here, the relic radiation over here, should be so jolly similar to the radiation in this completely different part of the sky? How can that be? Again, I refer you to my lecture on Faster Than Light and would point out again that if the universe at the time that the relic radiation decouples from matter and travels all the way across a transparent universe dates from a time when the universe is 3,000 centuries old, then the light can only have travelled a distance, slightly unusual length unit coming up, a distance of 3,000 light centuries, also pronounced 300,000 light years. It's a large distance, but it's not that large when you consider the size scales represented by the entire 4π of sky, given how distant that is from us, given that there are 13 billion years of light travel time from us back to it. This is a real problem. If you look at this figure here, then the very bottom slice is supposed to correspond to a time pretty close to the hot Big Bang itself. That green-blue plane there corresponds to the relic radiation, when the radiation finally decoupled from the matter within the universe. And the size of the horizon at that tender young age of the universe, 3,000 centuries, are given by those little white regions there, corresponding to only a degree or two in size. So how is it that in completely different directions, it's as though the entire thing is in this amazing thermal equilibrium? How could that possibly have happened for regions of the universe that could never have been in causal contact according to the simple model of the hot Big Bang? This is indeed a big problem, and we know it as the horizon problem. You cannot make sense of this amazing equilibrium all the way across the universe if you believe in causality, if you believe in the finite speed of light. Something is missing from the jigsaw puzzle. And the person who first drew this to our attention is someone called Wolfgang Grindler. He is the first person who said there's a problem with the hot Big Bang model, and that was based on his studies of horizons carried out in the 50s. Wolfgang Grindler is a very interesting guy, by the way. He was born in Austria, but escaped Austria as a young teenager. He escaped the threat to Jewish children via the Kindertransport. Had he not done so, he may not have lived to an age as an adult when he could make fantastic contributions to astrophysics and to cosmology. He studied at the University of Liverpool and later Imperial. Then he went on to the US, and he was one of the founding members of the University of Texas at Dallas, who said in his obituary, listing all his many achievements, way more than I have time to mention today, that Rindler reached this distinction by way of a miraculous journey as a refugee through the darkest tragedies of the 20th century. By the way, Penzias, the guy I mentioned earlier, who made the discovery with Wilson of the cosmic microwave background radiation, he too was a Jewish refugee from Germany at the age of, I think, 6 or 8, something like that. So truly the Kindertransport saved some precious lives, sadly not all, but these people went on, despite that start in life, to do some wonderful things. So now let's think about what's the matter in the universe, and indeed, let's think about the matter that we see in much more recent times, much closer to us than that relic radiation that we've been talking about. This is a movie made by NASA using data from the Hubble Space Telescope. And as we analyse galaxies all across the universe, we see that they are moving away from us. The separation between galaxies is separating from us. These are pretty routine measurements to make. Let me tell you, we make use of something called the Doppler effect, which I described in that lecture, Unravelling Rainbows. It's dead easy to measure whether a galaxy is coming towards you or going away from you. This was originally pioneered by Slipher, but it was Edwin Hubble, after whom the Hubble Space Telescope is named, who systematically studied galaxies and figured out that they were moving away from us. They were receding from us in a way such that the more distant they were, the faster they were receding from us. And we can understand this in the context of a universe that is expanding, where the separation of galaxies increases with time. What does it mean for the universe to be expanding? Well, it truly means it is something based on measurement, repeatable measurement, carried out by observers all around the world, that galaxies, once you get away from the neighbours, galaxies are moving away from us, such that the further away a galaxy is from us, the faster it is receding from us. And we think of this as space, or indeed space-time, itself expanding. But it's really important to realise that we ourselves are not expanding due to cosmological expansion. We may be expanding if we're eating too much ice cream, but actually the chemical bonds that hold our bodies together absolutely dominate over the Hubble expansion, as this cosmological expansion is called. The solar system is not expanding. The gravitational bonds that keep together all the planets orbiting around the sun absolutely dominate over the Hubble expansion. Very local galaxies indeed don't obey the Hubble expansion, the Hubble flow exhibited by more distant galaxies. And to show you, so you do get to see one pretty spiral galaxy today, this is Andromeda, Messier 31, our nearest pretty galaxy, imaged by my friend and colleague Stephen Lee, very, very similar to the Milky Way. That one is moving towards us. We are moving towards it. We are on a collision course with it. Gravity is dominating over cosmological expansion. With apologies for the cliffhanger, what happens when galaxies collide, as that will collide with us, is something that we're going to be studying in my lecture in January on the formation of galaxies and structures in the universe. But now let's think a little bit more about the fate of the universe. Let's imagine a box containing, say, 1,000 galaxies or 10,000 galaxies. Doesn't matter, but let's keep the same number together. If you plot the size of the box that you need to contain all your galaxies, then the measurements that are made of receding galaxies, plotted against time, is seen to increase. And if it increases at a rate that falls and falls and steadily falls, then the universe has got enough galaxies inside it to comprise what we refer to as a critical density of stuff in the universe. But now let's imagine that we make all those galaxies much, much more massive. Let's make each galaxy, say, 100 times more massive than we first thought of. If that's the situation that you're dealing with, then gravitational attraction is going to cause the fate of the universe to be very, very different. Again, the y-axis still contains the size of the region of the box containing 1,000 galaxies. But if you've massively increased the gravitational attraction, then ultimately all the momentum of the galaxies flying away apart from you, that will be dominated and won over by the gravitational attraction pulling them back in, if you've got enough density. And that is something that, if that happens, then what begins as a big crunch at the start of, what begins as a big bang on the left of this plot at the earliest of times, ends in a big crunch on the right-hand side of the plot. That's what happens if there's too much density in the universe. If you've got too little density in the universe, then the separation of your galaxies, the size of your box that you need to contain 1,000 galaxies, increases and increases and increases. That's what happens if you've got too little density. And which fate of the universe, which of those three fates I've just outlined, depends crucially on what the contents of the universe are. But in turn, how dense the universe is crucially affects the curvature of space-time itself. In my last Gresham lecture at the end of last year on spacequakes, I talked about how Einstein had demonstrated with his theory of general relativity that if you've got mass, then space-time is curved. And John Wheeler, who's pictured here, pointed out very pithily that if you've got curved space-time, then that tells matter how to move, but matter, having mass, tells space-time how to curve. So how much matter we've got will crucially dictate the curvature of space-time on sufficiently large scales for this analysis to be meaningful. So if we now go back to the cosmic microwave background, the different size scales that we see here, which is the different colours, correspond to slight variations in temperature. How large these are on the sky depends on the geometry of the universe. How can I be so confident saying that? Well, depending on what you think the geometry of the universe is, whether it corresponds to the critical density situation that I talked about first of all, which actually gives you a flat geometry. And a flat geometry is that described by Euclidean geometry. And Euclid, even if you've never met him, will describe the kind of geometry that you'll have learnt at school about number of angles in a triangle adding up to 180 and all that kind of good stuff. That's flat geometry. And that's what we get if you have a universe with a critical density of stuff in it. And whether you've got too lower density and you have a so-called open universe, or too much density and you have a so-called closed universe, will alter the size scales on which you see that multicoloured porridge. Now, those points that we looked at earlier were about a degree apart. They're measurable in lots of different ways. Everyone agrees on the numbers. That angular power spectrum that I said you could construct by a histogram of paintbrushes, which we know as a power spectrum of cosmic anisotropies. The angular size on which those variations occur arise from a very specific physical process. And it's just sound waves, acoustic waves in that early primordial plasma. All of the balloon flights, all of the satellites that I've referred to, always find that peak occurs pretty close to a degree. And that peak, that strongest peak there at about a degree, is a sound wave. It corresponds to the speed at which ripples could propagate at around the time the universe was cooling just enough so that matter and radiation would decouple and radiation could propagate unhindered through the transparent universe. Now, sound speeds and sound waves are actually pretty easy physics to understand if we know pressures, if we know densities. And there are very good reasons to say we know what those are at the time at which the cosmic microwave background radiation was emitted. So if you know the physical size scales on which those processes are happening, then you can invert to say, well, what are the angular scales? And then you can say, well, do we have a flat universe, or where parallel lines stay parallel, or do we have a closed universe, or do we have an open universe? In fact, all the distances and measurements that we can make, folding in the parameters that we understand at the time the relic radiation was emitted, are completely consistent with having a flat universe. In other words, implying that our universe is indeed at a critical density. But this leads to another problem, every bit as big as the horizon problem that I told you about a few minutes ago. Approximate flatness now, which is what the cosmic microwave background angular studies all seem to indicate, implies extremely tight constraints on how flat the universe was previously. It turns out from essentially Einstein's equations and the Friedmann equation, which governs the energies and the expansions that are involved, that the universe is balanced on something of a knife edge. If the universe is near critical density but very slightly off it, then give it a bit of time and we'll be miles away from having a universe that is nowhere near resembling a flat universe. And so if we're seeing a universe now that is approximately flat, in the past, we must have had a very, very extremely flat universe. How can that be? The universe does not like instability. Do we have a flatness problem? I'm afraid we do. So we normally denote the ratio of the actual density in the universe to this critical density by the Greek letter, capital letter omega. And so if we have a truly flat universe where we have got critical density, we say omega equals 1. But here's the thing. If you've got a universe that's dominated by matter, then the rate at which the difference between omega and 1 increases with time is given by this proportionality here. It goes as little t there is the age of the universe. So the age of the universe to the power of 2/3, which is a bit like 1, if you have any difference at all between the density of the universe and the number 1, the critical density, it's just going to spiral out of control. It's going to be extremely unstable. So if you say that the universe is, within, say, 1 or, 1.5 or something of being the critical density now, you are necessarily requiring that the density in the past was such that the difference between the actual density and 1 was within 10 to the power of minus 18. That's an extremely constraining and tiny number when you allow for the fact if we were a bit different from it, the universe would be way different. It would be nothing like flat now. Nature likes stability. If you've got a ball in a valley, it will be stable there. If you've got a ball on the side of a mountain or the side of a valley, gravity will take over. Gravitational potential energy will turn into kinetic energy for the turquoise ball. Nature wants to attain stability, such as the picture we have on the right. But it's as though the situation we're in is saying we're on this knife edge. If we had a perfectly critically dense universe, then we'd stay that way forever. But if we were even a tiny bit different, tiny here meaning 10 to the minus 18, vumph, it would scale away as the age of the universe to the power 2/3. This is very, very unstable. We would be requiring that at the earliest times, the ratio of the density of the universe to the critical density is between those two numbers. And so the fact that this seeming fine-tuning is required is a bit strange and a bit problematic. So we know this as the flatness problem. And it is uncomfortable within the simple, original, hot Big Bang model. Taken together with the horizon problem, we've got two big problems for Big Bang cosmology. The solution to both of these problems, and some others that I'll be describing in my next lecture, is something called inflation, not the economic kind, but the cosmological kind. And the explanation for this we owe to someone called Alan Guth, who was based at Stanford when he proposed the resolution to the horizon problem and the flatness problem, since based at MIT, the Massachusetts Institute of Technology. And what he proposed was that at the very earliest times, tiny, slender fraction of a second, something like 10 to the minus 34 seconds since the Big Bang, there was a brief but astonishingly accelerating expansion of the universe, which looked, this is just a cartoon, which gives you a sense of an original, very, very small region when expanded with tremendous sub-second rapidity, led to a region that got expanded to way, way bigger than the size of our observable universe. Now, if this sounds far-fetched to you, I'd like to challenge you to read this original paper. It's in PhysRevD, it's open access, you can dial it up and you can read it. I reread this paper in the course of preparing for this talk, and it's an astonishing paper because it's astonishingly humble by this cosmologist. For a start, he's saying a possible solution to the horizon and the flatness problem. It was Landau who once said that cosmologists are often in error but rarely in doubt. There's a lot of doubt and a lot of honesty and a lot of humanity expressed in this paper. He talks through about the horizon problem and the flatness problem. And he ends saying, it solves a lot of problems, but there's this and there's this. And I just hope this paper will stimulate further study. Well, it certainly did. And I would like to assure you that inflation as a model is something that's taken very seriously the world over. I wouldn't want you to think that it's universally accepted, but variance on this essential theme of a very brief but a very acceleratingly rapid period of expansion totally expand a relatively small region of the universe, itself in local thermodynamic equilibrium, perfectly so, gets utterly expanded to be way bigger than the size of our observable horizon today, which of course is how you get the solution to the horizon problem of bit of the universe over there is jolly similar to the bit of the universe over there. Similarly, the flatness problem is solved in the sense that the stretching out of matter, think of it as the stretching out of the wrinkles of a balloon. You blow it up and it gets a whole lot flatter. The details of the process in that paper by Alan Guth and others that I mentioned, absolutely, the nature of the expansion is such that it drives the universe towards critical density. And so it's impossible to say, yes, the Big Bang is a really good paradigm for understanding cosmological evolution, unless we also factor in inflation as a solution to the horizon problem, the flatness problem, and other problems that I won't be mentioning today. These ingredients are crucial for interpreting measurements of the early universe and understanding the physical processes which led to a very homogeneous universe, giving us a lumpy universe with pretty spiral galaxies today. Inflation was absolutely revolutionary thinking in, I think it was 1980 or 1981. Really revolutionary thinking, taken seriously, an important part of our calculations today, not yet universally accepted, with some validity, by the way. There are problems, it solves some problems, it creates other problems. But it's absolutely part of active, ongoing research worldwide. More implications of inflation will be part of the next 2 lectures in this series on cosmic revolutions. But that's all for today on the early universe. Thank you.